Welcome to all the students. We are going to continue on battery charging and swapping. You have so far done much of the course. You have actually learnt how to do the full what is actually electric vehicle consists of. You have understood the basic economics, you understand all kinds of issue right in the beginning. In chapter 1 we talked about charging and swapping also there, and then we went on to get into more detail. The first thing that we did in chapter 2 was we tried to get into whether what is a basically kind of energy required, what kind of power is required, what is the speed RPM that is required, starting from a first principle, forgetting that it is electric vehicle. We looked at the vehicle dynamics, that is what we did, and we did a fairly comprehensive work on that. So, you actually figured out what is the speed of the motor, how does it influence everything, the power required, the energy required in a particular drive, the torque required. We looked at all these issues from theory point of view, and then we went into a detail of how to do what are the various subsystems that a vehicle has, and we came up with the subsystems consist of battery, motors and controllers and various other subsystems. We actually discussed that. We then started putting foundation for the batteries. We basically did the foundation work on the batteries, that what kind of batteries, why that kind of batteries, why NMC batteries or why NCA battery, what does batteries involve, how do you take these cells, what are the materials there, how do you take these cells and actually convert into battery pack. And we learned also about the economics of that, and then we went into details of battery design. In chapter 5 we got into that, well, you require thermal design, you require mechanical design, you require electrical design to be done, a BMS to be done, along with the cells. All this together become the battery pack design. Simultaneously, we also did chapter 6, where we went into detail on motors and controllers. What does it involve to design motors and controllers? While we did some basics, we also did fairly advanced stuff. What is the different regions in which motor works? How can we move from one region to another? How do we handle the complete motors and controllers? We did that. We have actually more or less done the whole course. This is the last chapter that we are coming to, battery charging and swapping. I had already in the first lecture I had actually mentioned that here we plan to do the EV charger introduction, whether charger is slow or fast, swapping. We look at both charging and swapping, standardization, onboard charger, public charger, bulk charger, and economics of public chargers in Indian context. This is what I had said we will do, and then we went into the EV charger introduction. I talked about basically what is a EV charger, essentially AC to DC converter. It has some metering and protection at the input, it has some protection at the output. Basically it is AC to DC converter, battery is directly DC. We also went into that besides all this, we need to worry about payment gateway in the charger, because you will have to pay for charging. We have to work about communication with energy operator, because the energy operator must understand how much power are you actually drawing. Normally the electric vehicles draw a very large amount of power, and this is a sudden load that is added. So, what does it do to the grid? This is of immense concern. We are not discussing that in detail, but we got into this, that this is what we will do. Then we went into the communication with the vehicle, that what do we really have to do with the communication with the vehicle, and of course, then the grid connector and the vehicle connector. We went into that. Then I gave an example of two chargers. One are set of AC chargers and a set of DC charger, both level 1 AC charger and DC charger, and what does it really consist of. I had done that. And then we talked about that we have to worry about charger efficiency, we have to worry about charger protection, charger power factor and charger cost. And finally, I had done onboard and offboard charger. What is an onboard charger? What is an offboard charger? Onboard charger is basically something that is sold with the vehicle. It may be fitted with the vehicle or it may be additional unit given with the vehicle, but vehicle carries that. Offboard charger is something that is put in public, you come and connect your vehicle for charging it. So, that is an offboard charger. This is what I had already done. Today, I systematically get into the charger. What is a slow charging or a fast charging? One of the very common thing that is often talked about, oh, we need fast charger, we need slow charger. Do we understand what is a slow charging or fast charging? So, the range of the vehicle we have talked about. What is the range of a vehicle? Range means once the battery is charged, what distance can it go? It depends on the usable capacity of the battery. And we have also talked about the usable capacity of the battery is actually the original battery capacity multiplied by state of health. Why state of health? Because battery capacity may have deteriorated over time. Initially, the battery capacity may be 1 kilowatt hour. After usage by about 500 times, it may become 0.9 kilowatt hour. And state of health captures what is the amount of deterioration. So, original battery capacity and state of health. State of health is between 0 and 1, it will keep on deteriorating, or percentage you can say, it is not 100%, 90%, 80%. Plus depth of discharge. This is an important parameter, because right from beginning that we have been talking about that we do not charge the way battery fully, we do not completely empty it. This is bad for the battery. We leave some, we charge up to a certain percent, maybe 90%, maybe 93, 95%. At the bottom also we do not ever empty it at all. This is not good for the life of the battery, and that was captured as depth of discharge. So, usable battery capacity is original battery capacity plus state of health plus depth of discharge. A very simple concept, and this is of course true for most batteries, but specifically lithium ion batteries. The batteries behave best when they are slow charged. I will say about 5 hours, which is 0.2 C. Remember, I had talked about that. 0.2 C is the best. The maximum life will take place. The minimum deterioration takes place for a single charge and discharge, if you charge it slowly and discharge it slowly. So, next important thing that we have repeatedly pointed out, that you must charge always at moderate temperature and also discharge at moderate temperature, around 25 degrees centigrade. The best behavior of a lithium ion battery is 25 degrees centigrade plus minus 5 degrees centigrade. Anything above 30 degrees, it starts impacting the battery life. Below 20 degrees starts impacting the battery life. And remember, this can be a problem, because you may have to operate at a very high temperature, it can become a problem. So, generally, therefore, at night time charging is considered quite good, because night time in India, it will be just the opposite in the West. In the India, it will night time, because it will get cooler and temperatures will be closer to 25 degrees centigrade. And but we have also pointed out the vehicles need to travel longer distance than its EV range. Suppose the batteries provide you only a 80 kilometer range and you need to travel more than 80 kilometer range, then there are two options, and we had introduced this. One is what is called fast charging. Fast charging is typically 1C fast charging, basically means in about 50 to 55 minutes you will charge an empty battery to full. Remember, the DOD is never 100%. So, 1C, suppose DOD is only 80%, so 80% of 1 hour. So, approximately 48-50 minutes it will take. but you can also charge at 3C, that is a real fast charging, and that is what you can do in 15 minutes. So, this is fast charging. Fast charging is defined that if you charge completely a battery in 15 minutes, 30 minutes, 45 minutes, even 1 hour will be a fast charging, whereas 3 to 5 hours is slow charging. So, since we have done the C rate for battery, I will say 1C to 3C or even higher 4C is fast charging. Anything 0.2C, 0.3C, 0.5C, 0.6C is slow charging. Okay? Then comes somewhere in between. So, fast charging is 1C and above, 1C, 2C, 3C, 4C. Slow charging is 0.2C, 0.3C, 0.4C, 0.5C. So, if the vehicle does not give you enough range and you need to travel more than what it range. So, one is of course, you can do fast charging, another is to do battery swapping. We have introduced this in detail, we will talk more about it today, later today. Now, remember that if you have run out of battery and you are going to charge, even if you charge in 1 hour, it is not good, you have to wait for 1 hour. So, you can't like drive to something like equivalent to petrol pump and then put for charge and wait there for 1 hour. Nobody will do that. You will 15 minutes, are you willing to wait? Maybe, even that is not desirable. So, maybe 10 minutes, or you bring it to a parking lot, you have parked it and gone for some other work, that time you may charge. You may go into a shopping mall, charge it, go for about 30-45 minutes, come back, or go and to a restaurant, finish something and come back. Remember that I had talked about that one of the standard called CHAdeMO is in Japanese, a Japanese standard basically says, now that we have put the vehicle for charging, let us go for a cup of tea. CHAdeMO. Cha is same as chai. Chai pee ke aaye. Let us go for a cup of tea. The other option I have right from beginning of this course we have been talking about is battery swapping. Battery swapping can be done between 2 to 5 minutes, and there now you can take out discharge battery and put a charge battery, and you can leave things. So, both these things we have talked about in the past. So, what is slow and what is fast charge? It depends entirely on C rate, does not depend on kilowatt hour or watt hour. It is 0.1C, 0.3C, 0.5C is slow charged. 1C, 1.5C, 2C, 3C, 4C is fast charge. So, I want to repeat that this is slow charging and fast charging. Does a 5 kilowatt battery charged at 1 kilowatt or 2 kilowatt is a slow charge? So, you cannot say my charger is slow charger. Well, if a charger output power is 1 kilowatt and you charge a 1 kilowatt hour battery, it is a fast charge. So, it is not related to the charger power, it is both the charger power plus the battery size that you need to take together determine which charging is slow or fast. The reason I am repeating this because a lot of people say, oh, I want a 10 kilowatt charger that will give me a fast charge. Well, 10 kilowatt charger will give you a fast charge for a 10 kilowatt hour or 5 kilowatt hour battery. What if the battery is 30 kilowatts? It is a slow charge. Okay. So, the power does not determine alone the slow or fast charge, power plus the battery capacity. So, for NEET, so typical battery size and fast charge. For example, typical two-wheeler battery size can be 1 kilowatt hour to 3 kilowatt hour. So, what does it mean? If you put 2-3 kilowatt battery charger or even higher, of course, it is a fast charge. If you charge at 500 watt or 800 watt or a 3 kilowatt hour battery at 1 kilowatt, it is a slow charge. A e-rickshaw battery is typically from 2.5 kilowatt to 5 kilowatt hour, maybe even e-rickshaw is 2.5 kilowatt hour to 3 kilowatt hour. Auto on the other hand is 3 kilowatt hour to 6 kilowatt hour, actually can be even 8 kilowatt hour. You must understand, and from there you can figure out what will be slow charge or fast charge. A small car will be 15 kilowatt hour to 30 kilowatt hour, whereas a large car battery will be 30 kilowatt to 75 kilowatt hour. Tesla kind of batteries are 70 kilowatt hour. Bus battery size becomes bigger, 100 kilowatt hour to 400 kilowatt hour. This is a typical size of these batteries in the vehicle. Now, of course, varies from manufacturer to manufacturer, but that is what it consists of. Thus, say one 10 kilowatt hour kilowatt charger will be of course fast for the 2-wheeler, 3-wheeler, but will be slow charger for 4-wheelers and buses. So, same charger can be slow charger or fast charger. A 20 kilowatt charger will be fast for 2-wheeler, 3-wheeler and even the small 4-wheelers, but for buses and large 4-wheeler it will be slow charge. A 50 or 100 kilowatt charger will be fast for most except maybe very large buses and trucks. So, essentially you have to understand what C rate you are charging, not in terms of the output power. The other important thing that we need to consider is battery size and currents at 1C. Let us cell voltage be 3.7 volt and let us say its current rating is x ampere hour. The battery cells are 3.7 volt, that is very typical for an MC battery, almost all of them are 3.7 volt. That is a nominal voltage. Of course, I pointed out that it can go up to 4.2 volts and in the bottom it can go to 2.8 volts, but nominal voltage is 3.7 volt. And the cells are characterized by what is the size of the cells in ampere hours. So, I say let us say x ampere hour, it can be a 5 ampere hour, can be 20 ampere hour, can be 50 ampere hour. There is something called internal resistance of the cell. The cell has an internal resistance. Now, this is important. Why is this the internal resistance? Because you can model an equivalent circuit for the cell as consisting of the cell with a internal resistance. When a current flows, I square into the internal resistance will be heat generated. IR will be the voltage drop through the internal resistance. Only the remaining voltage is going to go into the cell, or when the cell is giving out the same thing, there is a giving out power, a internal resistance will come into the picture and it will dissipate heat. So, I think it is very important if you understand that if the internal resistance is IR, the heat dissipated at 1C charge is equal to x square into IR, because x is the current rating. 1C means you are charging, discharging at x amperes. So, x square into IR is the heat dissipated. We both are charging and discharging at 1C. Now, each cell in the battery dissipates the amount of heat. If the total number of cells are y, the heat generated is x square into y into IR. This is the heat generated. I know Professor Kaushal had talked about it, but I am just wanting to repeat because I now want to look at the charger. As the total power or the pack at 1C is 3.7 into x into y, what is the percentage of heat generation? The heat generated is therefore x square y into IR, internal resistance, divided by the total power 3.7 into x into y, or x into IR multiplied by 100% divided by 3.7 of the total charge discharge power. So, certain amount of power is just lost in the heat. So, take some typical heat resistance. What is the internal resistance? For example, prismatic cell has an internal resistance, high internal resistance of 6 milliohms. Now, This is for, of course, low capacity prismatic cells, 15 ampere hour, 14 ampere hour, the cells that we commonly use for 2-wheelers or 3-wheelers. If you have something like 50 ampere hour cells, then the internal resistance goes down to almost 1.5 milliohms. So, you have to understand what kind of cells are you talking about, and from the data sheet find out what the internal resistance is. For cylindrical cells, it is much higher, 25 milliohm to 35 milliohm, much higher internal resistance. Pouch cell is small, 1 milliohm, 1.5 milliohm is quite common. Of course, pouch cells are not near, low capacity pouch cells are not there. You typically have maybe 30 H, 50 H, 60 H. Nowadays, the common cells that we are using, cylindrical cell of course is low capacity. Pouch cells and cylindrical prismatic cells, you talk about 50 ampere hour, 60 ampere hour or so, something like that. So, I actually calculated this for 1 C charge for a battery using 4 ampere hour cell, and I take cylindrical cell. So, I take 25 milliohm resistance, the percentage of power converted to heat is 3.8%. What did I do? I simply did x into IR into 100% divided by 3.7, where x was the current rating. So, if I take a 4 ampere hour cell into the internal resistance, which is 25 milliohm, multiplied by 100% divided by the 3.7, and that comes to around 3.8%. So, in a cylindrical cell, 3.8% will be the heat generated at 1 C. What will be the heat generated at 2 C? What will be the heat generated at 2 C? Anybody can answer to me? 4 times, 4 times, I square R. You are doubling the current, the energy loss becomes very high. So, you can see that if you use cylindrical cells and if you are working at 2 C, fairly high percentage of loss can be there. This is something that very often is not even understood. Also, there will be IR voltage drop will be considerable, because you are working with 25 milliohm resistance. For battery using 15 ampere hour prismatic cell, 15 ampere hour prismatic means 6 milliohm, still high, 6 milliohm. What is the percentage of heat generated? Well, it is much more. Though my milliohm has gone down, my ampere hour has gone up. So, is that correct? Probably I made a mistake here. 15 divided by 6, 15 multiplied by 6 divided by 3.7. So, 90 divided by 3.7. No, I probably made some mistake here. 15 multiplied by 6 milliohm. So, it is 90, but it is a milliohm. So, 900, and so 15 into 6 milliohm, 6 into 10 to the minus 3 multiplied by 100 divided by 3.7. So, it is 9 divided by 3.7. Well, if it is 9 divided by 3.7, it will be less than 2%. So, this is not right, this will be more like 2% or 2.5%. but earlier I had taken this as 50 ampere hour. 50 ampere hour it would have been higher. For a battery using 50 ampere hour pouch cells, the resistance goes down to more like 1.5 or something like that too. In that case, the heat generated is only 2%. So, you can understand that cylindrical cells do generate considerable amount of heat. These do not generate as much heat. Now, at 2C the power will double, but heat dissipation will go up by 4 times. So, the percentage power will double, heat dissipation will go up by 4 times. So, it will actually double, not go by 4 pi. 3.8 will become 7.6, this will become about 4% and this is also 4%. So, this is something that we have to remember. This is the heat dissipated simply by charging. So, saying that I want to charge fast, I want to charge fast, remember fast charging dissipates a lot of heat and heat has to be taken out. Heat hurts the battery. Remember that if there is a heat and if it is not taken out, it will increase the temperature of the battery. Once it increases the temperature, its life will be very badly affected.